Okay, so here we're looking at the concept of the del operator and the gradient. So we can come to this normal analogy, a well-used analogy of a hill, or in this case, a parabolic surface in 3D. So I've got a Desmos representation here. It's mathematically represented by this function here. And we can imagine when we are trying to find the gradient of this function in 3 dimensions, we can imagine that we're sitting at the base of this little parabolic surface. And if we wanted to find the gradient, we would mathematically represent it using the del operator. We go del f, it would be del fx, y. Here the del operator is the partial derivative with respect to x in a vector format. Now, if we apply this del operator to our function or scalar field f, now this could represent a scalar field here. It could be temperature, where we have high temperature around the outside and low temperature in the middle, if you were to look at it purely in the xy plane. And if you apply this del operator to this scalar field, it would look something like this. And you have the del operator, which acts as a vector, and you're applying it to a scalar field. Now, if we multiply this out, we get a partial derivative with respect to x on x squared plus y squared, so you're left with 2x in the first part of our vector, then partial derivative with respect to y on our scalar field again, and we get 2y, and since we have no z component in our scalar field, we get 0 in this last component. Now, what this actually means here is it's actually given us a vector that's dependent on x and y that tells us the direction of the steepest increase of this function. So if you're going to stand at this very base down the bottom here at this black circle, and you were to spin around, this function here, if you're looking around 360, looking for the steepest and the most amount of work to get up the hill, this function here would give you the direction of the steepest increase. So if I just plug in a point here, we might go x is equal to 1, y is equal to 1. In this case, that would be right about here. And we sub that in, we would get 2, 2, 0. So this is the vector that points to the steepest increase. Now I've plotted this down here on the Desmos again, and this vector is here in the green. So we can see that if you're at that position, 1, 1, in this curve, this green arrow points in the direction that you would have to go up this parabolic surface in the steepest direction. In a more applicable scenario, if this was a scalar field representing temperature, this would point in the direction of the greatest increase in temperature. Seeing as that temperature is the highest at this outer region, this vector would point in the direction of this greatest increase in temperature.